center of mass. Every physical system has associated with it a certain point whose motion characterizes the motion of the whole system. When the system moves under an external force, then this point moves in the same way as a single particle would move under the same external force. This point is called the center of mass of the system. The motion of the system can be described in terms of the motion of its center of mass. Center of mass of a two-particle system. Consider a system of two particles of masses m1 and m2 and having position vectors r1 and vector r2 with respect to the origin O of the coordinate system. The position vector rcm of the center of mass of this system is given by vector rcm is equal to m1 vector r1 plus m2 vector r2 upon m1 plus m2, or m1 plus m2 into vector rcm is equal to m1 vector r1 plus m2 vector r2. Thus, the product of the total mass of the system and the position vector of the center of mass is equal to the sum of the products of individual masses and their respective position vectors. Let vector F1 and vector F2 be the external forces acting on M1 and M2 respectively. There will be internal forces vector F12 and vector F21, which the particles exert on each other by Newton's third law. Vector F12 is equal to vector minus F21, or vector F12 plus vector F21 is equal to 0, equation 1. So, the sum of internal forces is 0. This is true even if the system consists of any number of particles. The total force on particle of mass m1 is vector F12 plus vector F1 if vector v1 is the instantaneous velocity of the particle of mass m1. Then, according to Newton's second law, d upon dt m1 vector v1 is equal to vector F12 plus vector F1, equation 2. Similarly, for particle m2, we have d upon dt m2 vector v2 is equal to vector F21 plus vector F2, equation 3. The total force acting on the system is given by adding equations 2 and 3. d upon dt m1 vector v1 plus d upon dt m2 vector v2 is equal to vector F12 plus vector F1 plus vector F21 plus vector F2, or d upon dt m1 vector v1 plus m2 vector v2 is equal to vector F1 plus vector F2, since vector F12 plus the velocity of a particle is defined as the time rate of change of its position vector. Therefore, vector v1 is equal to d upon dt vector r1 and vector v2 is equal to d upon dt vector r2. Therefore, vector f external is equal to differentiation of m1 d upon dt vector r1 plus m2 d upon dt vector r2 with respect to t. This is equal to differentiation of d upon dt m1 vector r1 plus m2 vector r2. Vector f external is equal to d square upon dt square m1 vector r1 plus m2 vector r. Equation 4. Multiplying and dividing the right hand side of equation 4 by m1 plus m2, we have vector f external is equal to m1 plus m2 d square upon dt square m1 vector r1 plus m2 vector r2 upon m1 plus m2, or vector f external is equal to m1 plus m2 d square vector r cm upon dt square. Equation 5, where vector r cm is equal to m1 vector r1 plus m2 vector r2 upon m1 plus m2. Equation 6. Thus, equation 6 gives the position of center of mass cm of the two-particle system. The center of mass moves like a particle of mass m is equal to m1 plus m2 under the influence of the net external force on the system. The internal forces cancel out in pairs. Equation 6 expresses the center of mass in the vector form. The x and y components of the equation 6 can be separated to give the coordinates of center of mass as x is equal to m1 x1 plus m2 x2 upon m1 plus m2. Y is equal to m1 y1 plus m2 y2 upon m1 plus m2. The center of mass of two-particle system always lies between the two particles and on the line joining them. If the center of mass of the two particles were at the origin, then vector r cm is equal to 0. Therefore, m1 vector r1 plus m2 vector r2 upon m1 plus m2 is equal to 0, or m1 vector r1 plus m2 vector r2 is equal to 0, or vector r2 is equal to minus m1 upon m2 vector r1 is equal to 0. Thus, if r1 is negative, then r2 is positive. It means if m1 lies to the left of the origin, that is center of mass, then m2 lies to the right of the origin. If m1 is greater than m2, then vector r1 is less than vector r2. Thus, the center of mass of two-particle system lies closer to the heavier particle. If the masses of the two particles are equal, then vector r cm is equal to m vector r1 plus m vector r2 upon m1 plus m, or vector r cm is equal to vector r1 plus vector r2 upon 2. X is equal to mx1 plus mx2 upon m plus m, or x is equal to x1 plus x2 upon 2. Y is equal to my1 plus my2 upon m plus m, or y is equal to y1 plus y2 upon 2. Center of mass of n particle system. Consider a system of n particles of masses m1, m2, m3 up to mn, and let their position vectors be vector r1, vector r2, vector r3, and up to vector rn respectively. If vector rcm is the position vector of the center of mass of the system of n particles, then m1 plus m2 plus m3 plus and so on up to mn. Vector rcm is equal to m1 vector r1 plus m2 vector r2 plus m3 vector r3 plus and so on up to mn vector rn, or vector rcm is equal to m1 vector r1 plus m2 vector r2 plus m3 vector r3 and so on up to mn vector rn upon m1 plus m2 plus m3 plus and so on up to mn. Vector rcm is equal to summation of mi vector ri from I is equal to 1 to I is equal to n upon m. The position of center of mass depends upon the shape and size of the body and the distribution of its mass. The center of mass of the body may lie within or outside the body. The net external force applied at the center of mass produces only linear motion but no rotation. The motion of the center of mass represents the motion of the body as a whole. Therefore, we can replace the whole body by a single particle located at the center of mass. Motion of center of mass of a system. The center of mass of a system is a point where the whole mass of the body is concentrated. Therefore, m vector r cm is equal to summation of mi vector ri, equation 1. Here, mi is the mass of the ith particle and vector ri is the position vector of the ith particle with respect to the origin O of the coordinate system. Differentiating equation 1 with respect to time, we have m d vector r cm upon dt is equal to summation of mi d vector ri upon dt, or m vector v cm is equal to summation of mi vi, equation 2. Here, vector vi is equal to vector dn upon dt is the velocity of the ith particle and vector v cm is the velocity of the center of mass. The acceleration of center of mass is given by differentiating equation 2 with respect to time. We have m d vector v cm upon dt is equal to summation of mi d vector vi upon dt, or m vector a cm is equal to summation of mi vector ai. Here, vector ai is equal to d vector vi upon dt is the acceleration of ith particle and vector a cm is the acceleration of the center of mass. The equation of motion for ith particle by Newton's second law is given as mi vector ai is equal to Fi, where Fi is the net force on the ith particle. Since internal forces on the particles cancel out, m vector a cm is equal to net external force on the system of particles. Or m vector a cm is equal to vector f1 plus vector f2 plus vector f3 and so on up to vector fn is equal to summation of vector fi, or m vector a cm is equal to summation of vector fi is equal to vector f external. Thus, the vector sum of all the external forces acting on the system is equal to the multiplication of total mass of the system and the acceleration of its center of mass. The center of mass moves like a particle of mass m is equal to summation of mi under the influence of net external force on the system. Motion of the center of mass of a body cannot be affected by the internal forces. Momentum conservation and center of mass motion. Consider a system of particles of total mass m. The net force acting on the system is external force vector F external. The acceleration of center of mass is ACM. M vector ACM is equal to vector F external. If vector F external is equal to 0, then m vector ACM is equal to m d vector VCM upon dt is equal to 0. That is, vector VCM is equal to constant. Equation 1. Thus, in the absence of external force, the velocity of the center of mass of the system is constant. The velocity of center of mass remains constant when no external force acts on it. Therefore, m vector VCM is equal to constant, as m is constant. m1 vector v1 plus m2 vector v2 plus m3 vector v3 and so on up to mn vector vn is equal to constant. The total linear momentum of a system of particles is constant if no external force acts on the system, which is the law of conservation of linear momentum. Examples of center of mass motion. Explosion of a cracker or a shell. Initially, the cracker is moving along a parabolic path. While in flight, it explodes. Each fragment will follow its own parabolic path, but the center of mass of all the fragments will continue to be along the same parabolic path of the shell as before, because there was no external force and explosion is caused by internal force only. Motion of Earth-Moon system. Moon goes round the Sun in a circular orbit. The Earth goes round the Sun in elliptical orbit. So, the Earth and the Moon both move in circular orbits about their common center of mass, describing an elliptical orbit round the Sun. Here, Earth and Moon form a system, and Their gravitation force of attraction is an internal force, but Sun's attraction on both is an external force acting on their center of mass. Center of mass of a rigid body. The center of mass of a rigid body is a fixed point with respect to the body as a whole. Center of mass depends on 1. The geometrical shape of the body and 2. The distribution of mass. Center of mass is a point that represents the average location for the total mass of the system. Position of center of mass. The center of mass of bodies with symmetrical shape and uniform mass distribution lies at its center. For example, for a long thin uniform rod, the center of mass is at its geometric center. A thin circular ring or plate, circular disc, center of mass is at its geometric center. For three-dimensional objects with symmetry like sphere, a right circular cylinder, a cube, etc., the center of mass is at their geometric center. The center of mass of a body with non-uniform mass distribution and irregular shape does not lie at its center. For example, in a triangular plate, the center of mass is at the point of intersection of the three medians. For a right circular cone, the center of mass is at a distance h/4 from the base, where h is the height of the cone.